All right, so we talked about continuous and categorical predictors. So if the predictor variables are continuous or are different levels. Now we are talking about if my response variable is continuous or discrete. So far, we only looked at continuous responses. But what do you do with if your response itself is discrete? And this can be answered in the classical GLM, Generalized Linear Modeling Framework. So let's look again at the assumptions for a linear model. So here's a linear regression with a continuous predictor, but you can also think of ANOVA or just comparing two groups, or here three groups, maybe at -1, 0, and 1, where you predict three different means. This would be kind of the same framework, just with in an ANOVA framework. And there's some assumptions involved. All the differences, so all the observations should be independent. They should follow this linear model, and the residuals here should be normally distributed and also not change across the whole range here. Or in an ANOVA type, the variance shouldn't be different for the different levels of the predictor. Right, so each kind of group would have the same residual variance. However, if we do not have a continuous response, but for instance, a discrete response where the response is either 0 or 1, for instance, we have a species present, yes or no, you can forget about all these assumptions here. I mean, sure, they should be independent. However, all the other assumptions here are not met with a linear model. For instance, I mean, the trend here itself does definitely not follow a linear line. Also, if you think of, oh, maybe the line just should be the mean occurrence, so it can be 0.5 or whatever, but still the model wouldn't make any sense because it would predict mean occurrences or probabilities which are either larger than 1 or smaller than 0. So the mean regression line wouldn't make any sense here. And also, if you look at the residuals, both here at the lower end, all the residuals are small. And also at the higher end here, all the residuals are small. However, in the middle, all the residuals are large. Right? So there's a very clear trend about the residuals from small to large to small. But we can solve this problem by both changing the deterministic part of the model and also the stochastic part. So instead of using a linear regression model, you need a regression curve mu of x that kind of actually is in the respects the boundary of the data. So this S-shaped curve here, the mean regression line would describe probability of occurrence, and it is bounded between 0 and 1. And also the stochastic part, here you would have to come up with a distribution that only can take 0 or 1 values, and yeah, depends here on the mean prediction. So this would be maybe the probability of occurrence. Yeah, what kind of models would be fit here? Well, theoretically, especially in the Bayesian context, you can come up with any mathematical form of a curve that has this S shape here. And it would be potentially nonlinear in its parameters. I mean, here it is also nonlinear in the predictor, but it could also be nonlinear in the parameters. However, we couldn't kind of limit ourselves to a subset of all these nonlinear models where the framework still is meaningful. So generalized linear models are described by a special case of nonlinear models, where we start with a linear model. So there's always a linear model at its core. Here I call it eta of x to distinguish it from mu of x. So there's a linear part at its core, but it's transformed with some function f to the response scale. So here some linear regression line like we have seen before here. This can be kind of squeezed into the reasonable range here by some function. So this defines a framework, very specific framework. So some linear model at its core. But why are we doing this? Why can we not kind of come up with any model and fit this with maximum likelihood or MCMC or whatever? And the answer is these GLMs are comparably easy to use, and also their structures are meaningful. So when I have a positive relationship here, a positive slope in a linear part like this, then I know that this kind of translates to this positive S-shaped curve. So the parameters or the sign of the effects actually have a meaning, which is not the case if I just try to come up with any kind of nonlinear model that fits the data best. And also, terms like interactions between variables and so on, they are still meaningful and can be interpreted similarly to what we know from the linear modeling framework. So let's go through this step by step. We are starting here with the first and the second line, and then checking about the response scale later. So let's first look at the deterministic part of the model. You might know this term link function from the GLM framework. However, I must say the notation is a bit unintuitive. We start out with a linear model, and we want to squeeze this linear model here in the case of this 0-1 response into some S-shaped curve. Or we can think of it the other way around. We have some relationship here, and there's some function that is kind of the opposite of this function f that turns this nonlinear response into something linear. And so someone came up with a smart idea to call this direction here link function and not the other direction. So you can think of it, the link function connects or links the data level to the linear predictor. Whereas here we have the other way, sometimes it's called the inverse link, that kind of maps from the linear scale to the response scale. So here the inverse link in this case has to compress the linear model to the 0-1, and the link function here expands this regression curve from the data or from the response scale to the linear scale. So that's one half of the work is done. So we transformed the deterministic part of the model such that this mean regression line now, for instance, describes the mean occurrence probability. So what's the probability that the species occurs in response to some predictor, for instance, temperature? However, the data is still discrete. It's 0 and 1, and we need to come up with a distribution that defines the likelihood later on. So we have the linear model, we have the inverse link, and then we have to describe that the data is distributed around this mean prediction line. So here against this mean probability of occurrence. And here classically, we have the choice to involve discrete distributions. So for the response, we already have worked with this in the first lesson, where we had some binomial distribution. because the response was number of individuals surviving. However, still the parameters were continuous, right? So here we are only working with continuous parameters, but now we have the choice between discrete and continuous response values. And usually your data type already determines which distribution you should choose here. So there's some classical questions you should ask yourself. At least the first two are the most important. Is my response discrete or continuous? Here in this case, it was discrete. And also the second one, is it constrained or is it unconstrained? So here in the first line, both of these distributions are discrete. However, only the first one here has a lower and an upper boundary, classically the binomial distribution, whereas this other one here, the Poisson, is positive numbers, so it has a lower boundary, but theoretically no upper limit. Or if your response is not discrete, but your response is continuous, you have also this choice, the classical choice is beta distribution is bounded between 0 and 1, whereas the gamma distribution only has a lower boundary of 0. Another popular choice here would be a log normal distribution. So your this part here, which determines the likelihood for the parameters or the likelihood function for the parameters, usually your data should already determine what kind of distribution you are choosing here. Now we are stitching it all together. So what defines a generalized linear model? First of all, sure, you have some linear model at its core. And here you can involve different predictors. You can think of how to involve them. For instance, maybe there's an interaction. And all linear models are allowed, right? So you can be model all kinds of relationships we already have seen in the last lesson, ANOVA or ANCOVA and so on, linear regression. And here on this scale, you also define priors for your deterministic model parameters. Then you have this inverse link. So in this case, some function that squeezes the data or squeezes the regression line, and it is some function. However, usually we name it by the inverse. So in this case, so if you have a log link, g would be the log function, and then the inverse of this would be the exponential function here. This link function usually does not have additional parameters to estimate. Right, so this is just, I have a log link, I have a logit link, and so on. Usually this doesn't come with any additional parameters. And then you have your kind of mean prediction on the response scale. Then it's the third part, which distribution are you using? And this then defines the likelihood. So this kind of transforms it to the response scale, and this actually connects the prediction to the actual observations. And again, this is all not Bayesian statistics. This is the same for classical generalized linear models, with the only difference here that we can also assign priors here. Yeah, you have this distinguishing, or this difference between the G, which is the what's the name? Yeah, it's the link function. Thank you. And F is the inverse link. Usually, if you would write code yourself, so if you're coding in, for instance, Stan, or writing your own likelihood or whatever, you would go this direction, right? You have your predictor, you calculate the linear part, you transform it with your function F, and then you go to the likelihood function. So the logical order of computation would be not with the link function, but with the inverse link. So this is because in code you have to, go through it step by step, and this would be classical pseudocode. I mean, you would use some actual distribution here instead of just writing distribution, but otherwise that's basically how it looks like. I think for nimble injects, you can also specify it like this here on the right-hand side. I'm not 100% sure, but I think it's possible. However, for Stan, you actually have to go through the actual steps. I mean, we don't have to do this now because in BRMS, everything is done like your classical GLM. So here you would specify, okay, G of mu, so mu is the mean prediction, so mu is on this scale, and you know G of mu is on the linear scale. So G of mu is your linear model, and then the data Y is distributed around the mean prediction mu. Yeah, and this is how you specify it in a classical GLM, or also the same in BRMS. So yeah, here we are only using the link function. So how do I have to transform my response scale prediction to go to the linear scale? Yeah, again, this is quite unfortunate. I would say if like a couple of decades someone would have started this differently, then we maybe today would all work in this logical order of computation. But yeah, for some reason, it is not like this when you work with R and GLM and so on. You're working on the link function, not the other way around. Okay, let's go for one example. So here we want to model the occurrence of some species, this butterfly species. Classically, if you have several observations in different habitats, you have either yes or no if the species occurred, and you want to relate this to a predictor, for instance, temperature. Questions or research questions here could be, what is the relationship between temperature occurrence, or how much does temperature increase occurrence probability? Or you can also use it for prediction, like in species distribution models. So what is the expected probability for some new habitat? And you can use this for actual prediction. If you measure the environmental covariates in this new habitat, you can give a good guess for the occurrence probability. Yeah, so this is again the same overview, but here with actual meaningful values now. We have a linear predictor for temperature. So temperature is a predictor here, and we have a linear model for this with some intercept and some slope. However, this response here isn't meaningful, so we transform this into something between 0 and 1. Let's start with the actual function here itself. So that's again unfortunate. It's the logistic function, and it's called logistic regression. But the logistic function actually is only the inverse of the logit function, and this is the logit is the link function we are using here. But this is the actual computation that is done, right? So if you use this formula, you can transform this to this. So it squeezes everything between 0 and 1. And you can specify in GLM, you can specify this by the logit link. So this is the inverse of this function. So this would transform every value between 0 and 1 here to the linear scale, which can be arbitrarily large or arbitrarily small. And then once you have your predictions, you can connect it to the data. So mu here is on the response level. And then the actual data is either 0 and 1, and mu describes the mean probability of occurrence. So here we have the Bernoulli distribution, which is a special case of a binomial distribution, where the response can either be 0 or 1, and is described by this mean probability. Yeah, starting from here, going to there, what about priors, or what kind of slopes can I expect here? And here we assume that we have a mean-centered predictor. So here temperature is not actually 0 degrees, right? It maybe would be a bit cold for this butterfly species, but we mean-centered temperature here. So the actual observations of temperature in these habitats is somewhere between -2 and 2, because the mean is 0 and the standard deviation is 1. And now different slopes here, we assume in the same intercept here. So different values of slopes here give you different kind of regression lines, but on the response scale, this means also a steeper increase or less steeper increase of this S-shaped curve. However, the probability here at some point gets really, really close to 1, and it gets really, really close to 0. And this is here on the linear scale. Once you've reached the level of 4, this means basically a 98% probability of occurrence. So here, if the linear model has a value of 4, then this means here almost always the species is present. However, the opposite, if the linear predictor has a level of -4, then we are at almost never, so 2% occurrence probability. Imagine you have a slope with a value of 4. This means from 0 to 1, that's exactly this blue line here. So kind of extreme behavior of your linear model. So this might be highly improbable. So you can think of that your slope probably wouldn't be that extreme. So you can come up with meaningful priors, for instance, by specifying a normally distributed prior for the slope with a 0 mean and maybe a standard deviation of 1 or 2. Or if you think that there's a positive relationship, be careful how to choose the mean of this prior distribution. Again, if values get close to 4 or even larger than 4, this might produce unrealistic prior predictive models like this. So especially in the GLM context, I think prior predictive checks are quite meaningful, because these nonlinear transformations often transform your linear regression can transform them in a very extreme way, which might be unrealistic. So you can specify regularizing and meaningful priors here. I don't think there is any other distribution that would make sense here, because if you just have 2 outcomes and your mean regression line determines the mean probability of having occurrence here, and if you look at this part, that's already determined, right? So if your mean probability is equal to p, then your which is the predicted value p here, then the occurrence or non-occurrence probability is automatically 1 minus p. So if you just have this 0, 1 response, I don't think there's any other distribution that would make sense except the Bernoulli distribution. I know of other link functions, however. They are all kind of these S-shaped curves, but sometimes other disciplines prefer the probit link instead of the logit link. It is shaped a bit different, maybe, it's hard to explain, but it looks almost the same. For some reasons, other disciplines sometimes prefer the probit link instead of the logit. However, in all of these cases, the Bernoulli distribution here is actually the only one that makes sense. Okay, finally, let's look at the model fit, or let's first look at the complete model description here. So the deterministic part, so this is on the on the linear scale, and the stochastic part this here is happening on the response scale. We can write it as, so this is the link function, the logit of the probability is a linear model with temperature. Here I can specify priors. So here the intercept, if I'm using all of these kind of standard or classical and standard modeling choices, then the intercept can be safely chosen by BRMS. And here I would, for instance, choose a normal distribution, standard normal distribution here for the slope. If I kind of scaled my predictor value here, and then specifying this model here in BRMS is just the same as in GLM. So the Bernoulli function, the Bernoulli distribution, the link equal logit, this is, I think this is also default. I don't think you have to specify it. However, I always like to also write it in there, even if it's the default function, it would be chosen automatically just for me to see what kind of model I have fitted. Then the output here, if you look at the conditional effects plot, yeah, so this is a mean regression line and also some confidence intervals here for the deterministic model part. You get some output here, some intercept and slope values. However, these are now on linear level. And sure, I mean, because it is an S-shaped curve, the slope changes over the course of the predictor value here. So how does this linear slope on the linear scale now relate to this one here? Well, first of all, if I'm just interested if it's positive or negative, then I can also just look at this. Okay, yes, positive. And if you look at the confidence intervals here, it doesn't cover 0. So also the confidence intervals are far away from 0. So I am sure that this S-shaped curve also has a positive relationship. Yeah, each of these, or how is this here generated? Remember that kind of you're fitting this with MCMC. This means that you're getting many samples for intercept and slope, which are connected. And each combination of intercept and slope defines one linear model. And if you transform it, it also defines one of these S-shaped curves. Right, so each sample determines one of these S-shaped regression lines. And then here, the mean is extracted, or also the confidence intervals are extracted from the distribution for each value of the predictor. For each level of the predictor, you have a distribution. And if you extract mean and confidence intervals, you end up with this kind of display. So how do they relate? First of all, I mean, the intercept is some, yeah, here, so here's the linear scale, here's the response scale. The intercept has the same meaning here. That's the level here at the mean temperature, which is 0. And then the slope can be related, at least for one special case. What does it mean if there's a slope of 1.7? You can calculate the slope at mean or at a 50-50 chance, right? So wherever you have like the prediction of a 50-50 chance, here the slope of this S-shaped curve locally will have a slope of 1.7 divided by 4, or approximately divided by 4. So this is, I would say, the most accessible interpretation of this. Otherwise, you're going into the direction of calculating odds ratios, which becomes kind of weird and complicated. So yeah, I just want to say that, okay, if you estimate the slope of whatever, this is kind of the steepest slope which this S-shaped curve will reach. but the actual value is 1.7 over 4. Right, so the more steep this relationship here is, the more kind of curvy your S-shaped curve will be, with a maximum steepest incline at the mean level, or the mean prediction of 50-50. The model assumptions here are not as easy to test because, I mean, there's no normality assumptions of the residuals and so on. So you could also look at posterior predictive checks. So here, this was just the deterministic part of the model, but the posterior predictive check here can also include the stochastic part of the model. And so it predicts for each data point, it also predicts the occurrence or non-occurrence of a species, and then you get a histogram here of either the observed data, in this case it's light blue, and or the predicted data set, which is in dark blue here. So we have our linear scale. So here these values are purely determined by the intercept and the slope. Right, so here I have an intercept about, let's check this, 0.4. This means that at temperature equals 0, I have a value of 0.4, which is this, and then I have my classical slope. And the question is, well, I know the slope kind of changes over the whole course here because it is an S-shaped curve, not a linear curve on the response scale. So how do intercept and slope here translate to the behavior of this S-shaped curve? Sure, the larger the slope, the steeper the incline of this S-shaped curve. And just as a rule of thumb, you can transform this. So this number here, so the actual fitted slope divided by 4 is the maximum slope of this S-shaped curve. And this is always reached at the 50-50 level, right? So this 0.5 here. After this, the slope gets more shallow. Also below this, the slope gets more shallow, and the maximum realized slope is this estimated slope divided by 4, just as a rule of thumb. Yeah, we can look at the conditional effects plot, but I mean, if you have many data points, you can't tell if this is kind of meaningful or not. So you can also look at this posterior predictive checks where data is replicated from the model and the number of 0 and 1s, or the histograms are compared. If you look at observed versus predicted or residuals plots, this usually is not informative because here classically you will have this weird relationship. So we know residuals do not have to be normally distributed. There's no assumption about their normal distribution. And we have this kind of weird relationship anyway. And these plots are very hard to interpret. However, instead, you can look at binned residuals plots. So here, all of this information here along the x-axis here is binned in, let's say, 10 different intervals. And then if you have like these 4 points here in this lower interval, their mean is calculated. So this would be this point here. Because here in the middle, you also want the residual on average to be 0. So here they have like stronger deviations. Here at the upper part here, you only have lower variations. But for each kind of binned part of this x-axis, you want the residuals to be on average equals to 0. And this can be achieved by the binned residuals plot. Yeah, it's a function from the ARM package. You can extract the fitted values and the residuals and then plot this to see if they are on average equal to 0. Same data set again, but now think of you also have collected data in new warmer habitats, in habitats which might be too warm for the species. So what kind of relationship would you expect from the linear model, or also from the generalized linear model here? You would be interested maybe in an optimal temperature, so or the niche for this species, where you would have like higher occurrence, but in warmer and colder temperatures you would have lower occurrence. So if your data looks something like this, so you have occurrence in some intermediate temperature values, but also non-occurrences, but at low and at high temperatures, you only have non-occurrences. So you want to fit something hump-shaped, and you can achieve this by putting a quadratic term in the linear part of the deterministic model. All the other parameters here, our model parts are the same. Yeah, we just extending this linear model by a quadratic term, which then gives us this smooth shaped curve here. And here we see a negative parameter value for the quadratic effect, which means that it is a U-shaped curve. Sorry, no, it's a hump-shaped curve because of this negative value here. And on the linear scale, this would be a classical parabola, whereas on the response scale, after the transformation, this has this classical shape, bell-shaped, almost bell-shaped appearance here. This curve will always at some point go to 0, because here this parabola will go to -infinity at both ends. So this will always go very close to 0, but here it doesn't have to reach 1. Right? So the maximum height here is kind of also a parameter of the model. And this can be quite informative. So you can inform with this the maximum occurrence probability, but also some location parameter, which now can be done with a Bayesian framework, and it might not be so easy with a frequentist framework to extract this. So the question is, what is the optimal temperature for the species, and what is the associated uncertainty? That's the interesting part. So extracting the optimal temperature, you can either do this by eye. So here, this is where the occurrence probability is highest. It happens at this temperature, but since we are doing statistics, we are not extracting point estimates. We are always interested also in the uncertainty. And here, the cool thing is we can quantify this uncertainty correctly. We get the distribution of this optimal temperature. Okay, so each of these, each sample here defines one hump-shaped curve. This means each of these curves might have a different location of the optimum here. Now, with some calculus, you can derive where this extremum, where this peak is. So it's the extremum of this curve. And with some calculus, you can derive that it is B1 over B2 or minus B1 over 2B2. So you can directly calculate it from the parameters. So here from the quadratic parameter and from the other parameter. The intercept is not involved because it just kind of makes the curve either go higher or go lower. It doesn't shift where the optimum is. So for each sample, you can calculate this optimum. And then you can do this for every sample, and then you get a distribution here for this optimum. And from this, you can extract the mean and, for instance, maybe 90% confidence intervals. So for your question, what is the optimal temperature and what is the associated uncertainty? Here, the cool thing is you can derive something from the fitted model. It's nonlinear. It is a nonlinear, is a quantity in a nonlinear dependence of the parameters. So it's one parameter divided by the other. But you can always, get a posterior distribution for this quantity and extract all the statistics from that are interesting. So this would be a very simple species distribution model, which you can use for making model predictions about species occurrences. Here we had a species either occurring, yes or no. But now we are moving on to a also classical model binomial regression, but it directly comes from the logistic regression. Again, look at our example with a deer population, and we have some survival probability of some population. So we have data, what is the population number before and after the winter. Previously, we just estimated mean survival probability, but now we have a more complex research question. We want to relate this to the vegetation index and also the presence of predators. So here, vegetation index is a continuous variable and predator presence is either yes or no. So the field work didn't reveal any kind of abundances of predators, just if the predator is present. And yeah, now you would want to know if or how much vegetation affects survival probability. And yeah, if this is affected by predator presence as well. So a classical kind of ANCOVA type of model in a logistic or binomial framework. So for whatever linear model we are choosing here, again, we will have a log link, which gives mean survival probability of one individual. But now, since we not only have one individual, but because there are n individuals in each population initially, this now becomes a binomial distribution. It is a combination of Bernoulli trials for each of the n individuals. And then we get a bounded distribution between 0 and the maximum number or the number of the population. The binomial distribution itself is a bounded distribution, and it is the right, or one of the right choices here, because you can't have more individuals surviving than there are if there's no production over winter. So you actually reflect the boundaries of the data here. So this binomial distribution, it has a mean, it has a standard deviation. They can be directly calculated from the parameters here. There's also something called the beta binomial distribution, where the variance is increased, or you have an additional parameter for the variance if this is necessary. But usually in these type of data sets, the binomial distribution is sufficient. Importantly here, each observation, which is one population, right? Each observation is a different population. All of them can have different n. So you have different number of total individuals or initial individuals and survived. And this can be different for each data point. So this is the complete data set here. So the response is survived out of total. Vegetation here is a continuous predictor, and predator presence is yes or no. So I'm not going through this in detail now. It's just the linear part of this logistic regression is an ANCOVA type, where either just the intercept in an additive or also the slope changes with predator type. So this would be an interaction model. And now, yeah, in this case, because we have a categorical predictor, one of the variables is dummy coded. Yeah, in BRMS, you specify survived versus trials total. That's a bit different as in GLM. In GLM, you would say survived versus dead. But the same model is fitted. Here, you just have to specify survived out of the total number. And here relate this to the interaction of vegetation and predator. So this classical ANCOVA type of modeling. Here, if you fit the additive model first, this means I'm looking for the effect of vegetation, but I count that maybe predator has an influence on the survival probability. So this is an additive model. However, here on the response scales, these lines are not parallel because they are squeezed in the 0-1 range. However, if you look at the linear scale, both of these lines are parallel. So we advise looking for interactions or non-interactions in the GLM can be sometimes tricky and your eyes might deceive you. It's a question of, yeah, what you actually want to measure, because it will always kind of look like an interaction if you get close to 1 or close to 0, just because both lines have to be bent towards 0 slope at some point. So this model would not allow an interaction. So the slope here doesn't change with predator level. However, we could fit such a model where we have an interaction. So this means also here the slope in vegetation, or how much survival probability depends on vegetation changes with predator level. And here the effect now looks stronger. And on the linear level as well, you have a difference in slopes. Here, because the interpretation could be vegetation here has a stronger effect in predator habitats. So here the blue line or the green line, for instance, because shelter might be important, where it is not that important in non-predator environments. And for the binomial regression, now we do not usually have just 0 or 1 as a response, but many different response values. And then we can look at this classical posterior predictive plot to see if the predictions match the data well. Or again, we can have this classical, or no, this new plot we introduced, this binomial, sorry, this bind residuals plot, which can be informative to see if your model fits the data well. So what if we have the same data, but we lost some of the information? So we didn't record how many individuals there were before summer, before winter, and how many individuals there were after winter, but unfortunately, we just have the number, I don't know, 50% or like, yeah, 0.1 of the polyp. 0.1 is a very low number, but imagine you just have the fraction, right? So you just have the ratio and not the actual numbers. This is quite unfortunate because you're losing a lot of information there. Imagine you have one data point where you know, okay, 50 out of 100 individuals survived. This contains a lot of information because you're very certain that the average survival probability for this population was around 50%. However, if you just have another data point which has 2 individuals and one of them survived, you probably would also say, okay, mean survival probability is 50%, but are you certain about that? Right, so 1 out of 2 could also be just by chance. Even if your survival probability would be like 99, or let's say 90%, or would be just 10%, just by chance you could have like 1 out of 2 surviving. So it doesn't contain much information about this average survival probability. And if your data is just ratios, both of these data points are the same. So a lot of information is lost there. However, sometimes we just have ratio as a response. So how can we model that? Again, the deterministic part here is the same because we are still modeling a mean survival probability with some linear model. However, now the residual distribution is different. So the response here now is always a continuous value, as a value is on a continuous scale between 0 and 1. And here, classically, the beta distribution is a good choice. The beta distribution is parameterized a bit weirdly, so it has 2 scale parameters, alpha and beta, but we don't have to take care of this. Internally, brms will take care of all of these things. So instead of having it parameterized by alpha and beta, we are having it parameterized with some mean value. So the mean value is the mean survival probability, which is predicted, and we will have some shape parameter which defines some kind of standard deviation. However, there's just one drawback: exact values, so 0% surviving or 100% surviving in the data cannot be reflected by this beta distribution. But here, more complicated models can be used, for instance, zero-inflated models or the so-called ordered beta regression, which you can all kind of specify in brms without using additional packages. Yeah, and otherwise, I mean, it will look quite similarly. However, here, if you fit these models, the results will be slightly different from the binomial regression because it contains a different amount of information. Often I see kind of people using a classical linear model for this kind of data. And this might be fine if the proportions are not that close to 0 or 1, or also if the predictions do not get very close to 0 or 1, then this might be fine. However, I prefer actually modeling the constraint of the data because this relationship here, for instance, in the upper part, that at some point the proportion kind of, or the slope has to get more shallow because it can't exceed 1. This only can be reflected if you have a generalized linear model here. The next part, I'm not skipping completely, but I will be a bit quicker here, just give you the main points. Another problem, Poisson regression. It's named after French mathematician Poisson, not because we are having fish here as a data set, but I try to remember this always as like counting fish. Here you have observed numbers or population numbers and 2 predictors, which is temperature and pollutant concentration, and you want to model their influence. Here the the response is count, which means it must be positive, but it's not necessarily bounded. So here the linear model is connected with a log link, meaning the inverse of the log link is an exponential function. This just means that all the linear part here is transformed to something positive. So this enforces the mean population count to be positive, and then it can you can connect this mean population count to the actual observed data, which are numbers, and yeah, this is the mean predicted number of individuals. So we just have a interaction model here. Again, the linear model, you have either parallel lines or non-parallel lines, depending if you have an interaction, yes or no. However, on the response scale, something can look like an interaction, but it's actually not. So here we do not have an interaction, and still these lines do not have the same slope. Here, an actual interaction model would look different. Here, the on the linear scale, the slope changes, and this makes things look differently here on the response scale as well. But I want to talk about one thing, and this is model assumptions, and also in the GLM, depending on what kind of distribution you're using for the response, this comes with some model assumptions. For instance, if you use a Poisson distribution, there is an assumption that the mean scales the same as the variance. So it means for larger predictor values, you also have a larger scatter here. Right, so if you look at here, there's just a small scatter, and here at large values, there's a higher scatter. So in a Poisson, the mean scales the same as the variance, which means that the standard deviation scales as the square root of the mean. However, often your data looks differently, and we call this over-dispersed. So the spread grows stronger than just as this relationship. So it doesn't follow the assumptions of the Poisson distribution. But here we have a very easy solution, and it's just done by having a different distribution here. So instead of the Poisson, we are using the negative binomial, and it is the same as the Poisson, but with an over-dispersion parameter, which means that if this parameter is small, then let me think. Yeah, it's the inverse of this parameter, sorry. So this is the parameterization. If this parameter is small, this term here vanishes. No, sorry. If this parameter is small, then this term here is big. Yeah. So you have a scaling stronger than the Poisson. But if this parameter is big, then this term here vanishes, and then you're back to the Poisson. So just an additional parameter which allows you to model a stronger scatter in the data. And you can test this, for instance, just by fitting the model with and without, with Poisson and with negative binomial, and just comparing which of these models fits the data best. This brings me to the next model, and I think this is exceptionally cool. I like this a lot because we can also not have a kind of GLM type of model, not only for the deterministic part, but also for maybe the standard deviation. So look at this data set. We might suspect maybe there's a positive increase with the predictor here, but also the variance increases a lot. We cannot use Poisson, we cannot use negative binomial because the response is continuous. So we can't use a deterministic can't use a discrete probability distribution here. We also can't log transform this data because there's negative values. I mean, you could use an offset, but log transforming or using a log link would mean that we have this exponential function here fitting the data. However, if I want strictly a linear line here and I want to account for the increase in standard deviation, I can't use these classical solutions here. However, there's no reason against having a model of the standard deviation as well. So here in this classical model, the response is normally distributed around the mean prediction, which is informed by the predictor, but we can also let some predictors inform the standard deviation as well. And in the likelihood framework or in the kind of Bayesian framework, this is done very easily. So here we have two types of generalized linear model, or two types of transformation. The first row here, that's the same. We have a linear model. We have maybe a link function or not for the deterministic part. That's for the regression line. We have a linear model. Here we do not want to have something else. Here we just keep the linear model as is. So sometimes it's called the identity link for the mu. However, for the sigma, for the standard deviation, I'm also starting with a linear model here. So the standard deviation on the linear scale should be linearly dependent on the predictor. And then we're having a log link, meaning we are performing the inverse, so the exponential on this linear model to get something positive. This is necessary here, or often necessary, to guarantee that the standard deviation is always positive. And then we have a classical Gaussian distribution, which we already know from the linear modeling part. So all of this is basically a linear model, not a generalized linear model. The only difference is that here we have some additional model for the standard deviation, and this makes this a generalized linear model. This is how the model fit would look like if we just fitted a linear model without taking care of the standard deviation. You clearly see here, so this is the absolute value of the residual, and this definitely increases with fitted values. This is what we see here, right? So the spread increases, which also means that the residuals here will increase. So the assumptions for the classical linear models are not met, and also this looks really bad. However, we can fit this distributional model, and we can specify it like this. Here we use the bf command to define a brms formula. And here in this case, we just specify the classical linear model part and also say that the sigma is depending on the predictor value here. BRMS automatically then uses no link for the mu, but as default, a log link for the sigma to make the sigma always positive. And then we see here, okay, we get an intercept for the sigma and also a slope for the sigma. Yeah, and this model actually has a difference. So, I mean, this is just what we call a nuisance parameter. We are not actually interested in how much the sigma increases with x. We are just accounting for it. Here we would be interested just in the slope with x. And here this actually is different from the previous model we fitted. So this would be the correct model here, because the linear model assumptions are not in place, because we allow for a difference or an increase in the residuals. You can also look at how the sigma changes. Again, here on the linear scale, yes, it's linear. But on the response scale here, sigma increases along the whole range of predictor values. And also, yeah, the posterior predictive checks look better here. And if you look at the conditional effects plot, again, so this is displaying the deterministic part of the model, but displaying also the stochastic part of the model. This nicely accounts for the spread of the data. It's not that often that I would have a model like this. However, think about ANOVA. Classically in ANOVA, the assumption is that all the groups have the same standard deviation, and this often is not the case. And here you can also use this distributional model to make the sigma different in each group. So here, classical ANOVA with 3 treatments. C has a strong, large spread, which would also be a large variation in the residuals. And this can also be accounted for here with this distributional model, which I find pretty cool. It's very easy to do. Just one additional line in the formula. And here, this is something I regularly observe in data sets. This can happen, and you get better estimates potentially by accounting for this. Okay, we talked a lot about linear models. This meant that yeah, they all go back to, at the core, there's always some linear part here, some linear relationship, and it is transformed. However, sometimes there are just non-linear relationships we want to model, because maybe we have some process we want to fit, and we have a specific formula for this process, and this might be a non-linear. So this is typically experiments I am working with. We are looking at feeding rates of species and their density dependence. So imagine some experiment where we have maybe one predator individual, and we give this predator individual maybe 20 prey individuals and just count how many of them are eaten after 1 hour. And I'm sure the more prey you provide, the more it will be eaten. But the predator can only eat so much in a given time. So at some point, this relationship between offered number of prey and number of prey eaten gets more shallow. So this density dependent feeding rates is called the functional response, and it has a very specific form. It comes, or the parameters have a meaning and have a biological meaning. For instance, the handling time is how long it takes for the predator to handle one prey. And here we want to estimate these parameters from this very specific form, right? This comes from, yeah, from first principles, and we want to estimate parameters on such experimental data. This looks a bit intimidating, but it's actually it's not that bad. So this is the formula we want to fit. Additionally, we assume that the response is binomial distributed because we have integer numbers. And I must say it's kind of easy to model nonlinear relationships, because you directly can write down the formula into this line here. So you define a formula, you can name it whatever you like, BF define such a BRMS formula. And then we say the number of eaten is depending on N0. So this is the predictor, the number of available prey. And here are the parameters A and H. Here additionally, I specify that A and H do not depend on other predictors. So you're just fitting A and H. And you specify nonlinear equal true to tell BRMS that it's a nonlinear model function. Then I specify some priors. These are exponential distributions, so just a positive distribution. Could also have different choices here, but I specify lower boundaries here, and I just have to tell them, okay, it's a nonlinear parameter. And that's basically it. Then you can put this here in the BRMS formula. Yeah, additionally, I said, okay, family is Poisson because the response is integer values, count data, and I don't want to have an additional link function here, right? So I say link equal identity because this formula is already on the correct scale. I do not have additionally transform this. Yeah, and that's it. So you get estimates for your parameters. So here in this case, I wouldn't be interested in statistics, but in actual good estimates for this attack rate and handling time, these parameters with their associated uncertainty. And I can use all the nice BRMS functions to check if the model and the data match up quite nicely. One step, I'm doing one step more. I want to use this for hypothesis testing. For instance, if I have two different populations of predator, or if I have two different prey types, or if I have different experimental conditions. So think of, we have an additional categorical predictor for the experiments because they might be performed at different temperatures, and we have some hypothesis if the feeding behavior is different in warm experiments. I don't have to change this whole formula. I just can make these parameters A and H depending on temperature. In this case, temperature is a categorical predictor. And if I specify 0+, then this means we are directly fitting a low and a high, meaning a cold and a warm. So two parameters to avoid dummy coding, and I don't have to specify anything else here. So whatever kind of relationship you have here, you can additionally make the parameters depending on whatever kind of model. Also, if you have multiple predictors here. So potential complicated coding or relationships here can be handled very easily in BRMS. I mean, there's limits, but I was surprised to find out how this works here. And yeah, sometimes I'm fitting my data with BRMS instead of coding it all of this in Stan myself. So here, yeah, we see in higher temperature, there's more feeding or higher feeding rates than in low temperatures. Reflected that the attack rates here are higher in warm temperatures than in low temperatures. And we can also use the hypothesis functions to look if parameters are different. And here, the result was that in warm experiments, the attack rates are higher. This means the feeding increases stronger here at low densities. However, we didn't see any differences in handling time. So the maximum feeding rate here eventually will be the same. And you can use classical model comparison here as well. So what's Bayesian about it? First, the classical GLMs. I often have the same answer to this question. you get an exact quantification of parameter uncertainty. This, yeah, is important when you go beyond simple linear models. And also you get correct quantification of the confidence intervals, for instance, of the predictions. Here, these the predictions or the confidence intervals again are not done with the mean parameter estimates, but with a whole distribution of estimates and a whole posterior predictive distribution. Yeah, at least in a certain kind of range, you still can fit, or in a certain amount of complexity, you can fit nonlinear models by just writing any formula you want to test in BRMS. And the cool thing is you can do all of this in the same framework. And then you can compare models, do model testing and so on, all with the same functions. So again, all of this can be very nicely done in BRMS and is quite comfortable to use. Yeah, so even nonlinear models can be fitted, all kinds of GLMs with a wide range of possible link functions and distributions and so on. We've seen that we can potentially fit nonlinear models as well. However, in the kind of classical statistical framework, if you analyze data, you should stick to the GLM framework unless there's a specific reason to not do so, because the linear part in the GLM is useful and it's well known and it's interpretable. The difference to frequentist statistics, sure, is you can specify priors, but here, yeah, this has to be done carefully because sometimes it's non-intuitive, not as in a linear modeling framework. However, you can always use prior predictive checks to see if you messed up or if priors are meaningful. And here, often scaled predictors are really helpful. One final comment is you can use a model comparison to compare different GLM contexts or also different distributions. For instance, the Poisson versus the negative binomial. However, this only works if you have kind of two discrete distributions or two continuous residual distributions. You cannot compare a discrete versus a continuous residual distribution. This is unfortunately done much too often, but it is mathematically invalid. You will get an information criterion for the one and for the other one, and you can kind of calculate this and you will get some output, but this output will be usually quite meaningless because mathematically it's not possible to compare them. And then I'm continuing with some examples. Okay, I think I'm gonna skip the first one, or I'm just showing you the first one. The other ones I will do. And this is just a very simple comparison of means. So yeah, you have different fields or patches from two groups. One is nursery and rookery for slug populations, and you just count the number of slugs in each of them. And you want to compare, yeah, is the average slug population larger in the one or in the other? You can just fit a linear model there, or classical ANOVA, or it would just be t-test. However, the assumptions of your model, of your linear model, would be violated because yeah, if you will look at the residuals, they will look really weird because you have this lower boundary of 0 here, and here actually a Poisson distribution is a much better choice. You will get some output here for the mean in both of these groups, and you can check for the difference, which is, let me just check, the difference is almost 1 with a standard, with the confidence interval from 0.4 to 1.5. This is what the Poisson model predicts. However, if you just fit a linear model, you will get different values. You will get also a average average difference of almost 1, but the confidence intervals are much, much higher here. I think here the standard deviation is about 0.5, whereas it was just about 0.3 in the Poisson, so in the correct model. So even for this most basic model, right? So just comparing two means, modeling the data appropriately here with the Poisson can make a difference. Okay, so the next model is binomial regression. So I will first take a look at the data, and then I will tell you about what kind of model we are fitting. So this is from it's from a textbook where the data is provided in a GitHub repository, and we are looking at infection rates of mice. Yeah, so infection rates of mice versus a common parasite, and for different levels of exposure to this parasite, we get different infection rates here. So this is just the proportional data. However, we have access to the actual numbers here, so we can fit a binomial regression. So we have the dose, so that's the predictor, and here we have the numbers y out of n. So y is the number of infected, and n was the total population. And we have a specific research question. I mean, sure, we want to fit this classical model, so a linear model where infection rate is depending on dose, and we have a logit link, so a classical logistic regression. And we expect, sure, the higher the dose, the higher the infection rate. But we have a very specific research question: which dose is needed to infect on average 70% of the mice? So for which dose can we be sure that at least 70% of mice are infected? So first of all, we are just going to fit this model. It's a very classical framework here. So the number of infected versus the number of trials, so the total population, should be dependent on dose. And here I scale the response, which means I make the predictor mean-centered and standard deviation equals 1. And the stochastic part is classically the binomial with a logit link. So no prior for the effect of dose is given. However, we can use a prior here because we are at least a bit certain that dose has a positive effect and not a negative effect on the infection rate. So it shows here a mean of 1 and a standard deviation of 1 for the prior. But this is kind of very weak. We could also be more specific here because we do not expect there is a negative influence of dose on infection rate. Yeah, it's called crypto just because the parasite is Cryptosporidium. And I mean, the model is really, really very basic, and so there's not much to see here. We get a positive effect of those, and yeah, the confidence intervals are also the credible intervals are far away from 0. So this is all pretty standard. However, this is classically happening if we have a binomial regression and we want to plot the conditional effects. Because if we do not specify anything, what is happening here? The predictions here are plotted for a population number of 1 only. So it automatically sets all the trials to 1. And then the points just add the y values and also do not specify y out of, so 2 out of 10 or so survived. So here again, it took me a while to figure out how to do this correctly. I mean, if you just have a logistic regression with 0 and 1 outcomes, you can easily plot this. However, here, this is not the case. So first of all, I'm plotting this, just this response. Right? So here we are on the scale of between 0 and 1, and this is the mean expected infection rate. And now we add the points. So we here add the points. So the x-axis is those, and the y-axis is y over n. And this took me a bit to find out. I have to say inherit AAS. So the x's are not inherited from the previous plot. This took me a while to find out how to plot this with some ggplot magic. Okay, so now there's on the y-axis is the actual ratio of infected and plotted against the predicted ratio of infected. We can look at posterior predictive checks. For instance, the classical posterior predictive check here. So these are the number of observed responses versus the number of observed responses with the data. It doesn't look that good here. There's some structural difference, which could mean that we have been missing a predictor. But here we don't want to go further, and I don't know if the data set even contains another predictor. So we are fine here now. So I'm skipping this. And now we want to go to our research question. So what kind of dose is needed that we are sure that 75% of the mice are infected? So why not plotting a line here through the 75%? Okay. So let's check. We could kind of visually check. Okay, here at this point, the mean of 75% is reached. So we could check for one of these values here. I haven't found a good way to automate this. So I actually checked some numbers when this is actually reached. And I found that for dose equal 191, I'm closest to the average 75%. Right, so if we look at the fitted values for dose 191, I'm very close to the 75%. Or you could also look at the distribution of the predicted value. So that's just a slice through this distribution here. And yeah, this is how it looks like. However, there's just one disadvantage. What are we fitting here? Okay, at this level of dose, on average, they are 75% infected. But if you're interested in, well, am I sure that 75% are infected? Well, no, I'm just 50% sure, right? So I'm just 50% sure that 75% or more are infected, because this is just the mean here, and the probability distribution here larger than the mean is just 50%. So by slicing through the mean here, we actually did not answer our question correctly. So if the question was, at what dose am I quite certain that at least 75% are infected, I should look at the lower value of the confidence interval, of the credible interval. So here I think this is a 5% credible interval. And yeah, once I have this dose, I know, okay, I am maybe 95% sure that 75% are infected. And again, I didn't find a nice way to automate this. Maybe you can do a for loop to check something. I just played around with the number and see, okay, for which dose do I meet the lower boundary of the confidence levels here? And for me, this was 229. Here, the lower confidence bound is closest to the 75%. Oh, it's even the 2.5 quantile. So here this means I'm 79.5% sure that at least a ratio of 75 of the mice are infected. And so once we have this level of exposure, then I am whatever 97% sure that at least 75% are infected. So again, here I could kind of transform my research question into something I can derive from here, the posterior distribution. And here I could benefit from the fact that I very accurately can estimate these confidence bounds through Bayesian statistics. I mean, you can also, will get some confidence bounds as well for frequency statistics, and you could repeat this same kind of analysis. Here the kind of, I would say, trick was to think about what answers my question correctly, and it is not the mean, but it is the lower boundary of the prediction here that I should aim for. Okay, so moving on to the next data set. Here I will have count data. Oh no, it's not. Sorry, it's not count data. It is nonetheless integer data. So it's the weight of young chicklings measured, at different days. And since the scaling was done, I think rounded to the integer, so we only have like these integer values here. And we want to estimate what is the average daily growth. So if you plot this data here on the log scale and also limit this at some certain age, so only up to, let's say, the age of 15 days, you can observe that there's potentially linear increase on the log scale. Going after this, the model should be more complex, and there's also a model formulation for growth model. It's called the Bertalanffy growth function. So you could also use a nonlinear function to fit here, but we are keeping things simple for now, and we just want to model this initial phase of growth, which is potentially exponential. Right, so here on the linear scale, this could look like some exponential growth if you go up till the age of 15 days. And on the log scale, this would look like this, right? You would have this linear increase on the log scale. So we are just using a subset of the data until the age of 15 days. I mean, there's different kinds to model this. I must admit, using the Poisson model here is a bit of artificial because we can just use it because the data is rounded to the integer anyway. But we want to test for, we want to use this to check if the assumptions are actually met here, or if we have to use something which is over dispersed. So the model here, it's quite simple again. We have just a linear model. However, we are using a log link. And then the weight is Poisson distributed, so discrete distribution around the predicted mean. And the Poisson distribution does not have an additional standard deviation parameter. Here, the standard deviation is equal to the square root of the mean. So this is fixed in this Poisson distribution. Again, I can look at the default priors here. However, I don't remember why I specified the normal 0-1 prior here, I must admit. Yeah, I think it's a bit too uninformative because we know these individuals grow and don't shrink, right? So we could specify. Oh, all right, yeah, I did. Sorry, I forgot. I specified a lower boundary of 0 here. Yeah. And yeah, normally I would kind of also check this with prior predictive checks to see if the value here actually makes sense. But the important thing here, I want to communicate this. You can or you should specify boundaries if they are really necessary. For instance, here, yeah, we know there's no negative growth, so we can enforce to just sample from the positive part in this case. So let's check the model. This looks all fine. We have an intercept and a slope. And now we are looking at the conditional effects plots. So we have this exponential increase here. Right, so this is now, we didn't fit log weight to the model. We fitted weight with a log link. Right, so we didn't kind of log transform the data. This is not what we are doing. We are using a log link, which means that we are kind of exponentially transforming the predictor. I mean, conceptually, it's kind of the same, but technically, it's different, right? So we are not log scaling the response because we want to use the Poisson here. However, we are exponentially transforming the linear predictor. So we have this exponential increase here. Okay, yeah, what do we see? Okay, the standard deviation here of the residuals increases, but this is fine in the Poisson model, right? So the Poisson model, the standard, sorry, the standard deviation also increases with the mean. However, if you look at the posterior predictive checks, there's still some, I would say, very systematic deviation here. You can also look at the posterior predictive checks. So this is just plotting the deterministic part of the model. But if you look at the the stochastic part of the model as well, you see that this variation here is not reflected at all by the model. So this means we potentially have some overdispersion here. I think in frequentist stats, there's classical tests for overdispersion. Here, we could just fit a model that accounts for overdispersion and compare it to the previous one. So here we are fitting this next model where the variance scales differently, the variance scales stronger. And this is done here by the negative binomial model. So this is a Poisson model plus some additional overdispersion. So you have this additional parameter here, which is called the shape, which determines how strong this variance increases. And there's some standard prior given for this, so I'm not touching that. And then we are fitting the same model again, just with the negative binomial family instead of the Poisson family. Yeah, so remember also in GLMs, there are model assumptions. They are usually not that strong or not, yeah, no, that's not true. They're just different model assumptions than in the linear model where you have normally distributed residuals. Here, the assumptions for using a Poisson is that the variance and the mean scale in a very specific way. We have seen that the model here cannot reproduce what we find in the data. So this assumption is not met here with the Poisson. So we have to allow the model maybe some more freedom to have another variance mean scaling, a stronger variance mean scaling. And this can be done with the negative binomial distribution. I don't know why it takes so long, because I did not specify to use CMD stan R as a backend. Just fix that. Yeah, we fit the model and look at the convergence first. This looks fine. And now we see we get an additional parameter, which is the shape. So it's another distributional parameter, right? So if you fit just a linear model, you also get the sigma down here and the distributional parameters here. Now this shape parameter also appears down here at as distributional parameter. And these are the kind of deterministic model intercept and slope. So yeah, does this model fit the data better? If you just look at the deterministic model predictions, we can't tell. But if we include the stochastic part of the model, so here using posterior predict, then we see that that this increase in variation is represented better with the negative binomial model. And if we look at the posterior predictive check on the other one, yeah, here we see that the distribution of the actual observed data is much better represented than with the other one. So this was the other one for comparison. So here we see a structural mismatch of predicted and observed, whereas here we see a very good overlap. And then finally, we can do a classical model comparison by just comparing the model with the other one, with the leaf-on-out cross-validation. And here we see a yeah, a strong increase in model performance when using the what's the name? Negative binomial model. Okay, so we are happy with this model. So back to the research question. Why did we do this? Okay, we wanted to extract the daily growth rate. And so there is a daily growth rate involved with this. However, we have to do a bit of math here to actually get it. So this is the model we fitted. And so log of mu is a plus b times time. So this is the linear model, which means that on the response scale, we have to transform this to the, So we have to resolve this here by using the exponential on both sides of the equations to get here the mean prediction. Mu is, now we have an exponential function, right? And this can be resolved as exponential of a plus e to the power of b to the power of time. And now this here is our actual growth rate, right? So this is the kind of rate, the multiplicative, which the individual grows every day. And I think I have stressed this very often before. What we do not do is to extract the mean slope, so the mean b, and take the exponential of this. So we are not using exponential of 0.09. This is not the mean expected growth rate. No, we are using the full posterior distribution. So we can here draw the full posterior distribution. B time, this is what we're interested in. And we are kind of taking the exponential of this. And this is a distribution of the daily growth rate, and then we can extract its mean. So it's a bit different than the value here. I mean, here the difference is really small, but there is a difference. So always use the full posterior to calculate anything after the model fitting. So here the growth rate, that's the right one, and also the associated uncertainty. So the mean growth rate is, so each day the weight is multiplied by 1.196, and this is the same as a 9.6% increase in body weight each day. Yeah, this will be the last example now. I'm sticking with the same data set. However, I already said that using a Poisson here or negative binomial is a bit of artificial because the data is only integer because someone went there and rounded it, right? Usually we have scales which are much more precise than just to the gram. So why not use this kind of information? So imagine the measured response here was not integer, but were actual continuous value to the, I don't know, third digit or whatever. And we want to fit this model. Again, we are interested in the daily growth rate. Yes, and Beta said we only use the first 15 days. And this time, yeah, we have a continuous response. We can here directly fit the log of weight as a linear model, right? So this is log of weight. We want to fit a linear regression now. So that's the classic linear regression, just log of weight versus mean prediction, and this is a linear model. We can fit this, no problem. However, we already know that the linear model assumption with the residuals are not fulfilled. But let's fit it anyway. And then we are having a look at the model assumptions to see how a mesh specified model can look like. Because the next step, I want to accommodate for this non-constant variance by fitting such a distributional model. Yeah, we get an estimate. Again, here, this is really close to what we have estimated before on a linear scale here. However, now we are looking at the conditional effects to see if the data is represented well by the model. So this here is already on the linear scale. Sorry, this is already on log scale. As before, when just plotting the deterministic part of the model, we don't see much. But if we also include the stochastic part of the model, now we begin to see some mismatches. All right, so this is just a linear model here. So the residual variance is constant, which means that we overestimating the residuals here at the lower end, and we are underestimating the residuals here at the upper end. And this, for instance, reflects in some mismatch if you look at the posterior predictive checks here. Again, here's some classical, some systematic mismatch of observed and predicted. And if you look at the check model, so the output from the performance package, where you get all these plots nicely, we see definitely some mismatch here. And so here we see that the residuals increase, they get wider. And if you plot the absolute of the residuals, you see that so this line here should be constant and it's increasing. And again, here's so the QQ plot, this is really off. And also the residuals here are not normal. So just using the linear model here is a bad choice. It could result in biased estimates or bad estimates, especially also for the uncertainty. So we will fit a model that accommodates for this increase in variance. And here we could say, we just want to have a model where not only the mean, but also the standard deviation is a function of time. Time is the predictor here. So the model, we are not changing anything for the deterministic part here. However, we additionally allow a linear model here for the sigma, and it is associated with a log link to ensure that the sigma stays positive. Otherwise, we might sample from some parameter combinations of C and D that produce a negative sigma, and at this point, the MCMC couldn't continue sampling because it is just not defined. So this is the model we will be fitting. We can look at the default priors. Again, if you have like two model equations, you can combine them with a BF, so BRMS formula. I'm using the same model here. Log of weight is depending on time. And now also sigma is depending on time. So here the default priors, this is the same as before. But also now for the sigma, we get a set of priors, and this is noted here as dpar. This means distributional parameters. Okay, there's some value for the intercept. We can additionally define a prior for how much do we think the sigma increases with time. So for instance, yeah, is there an increase or is there a decrease? However, I chose very weakly informative priors now. Yeah, and you specify this here by d par equals sigma. And then we can fit the model. And it takes a bit longer to fit, a couple of seconds. So if we look at the model output, see, okay, family Gaussian, yeah, the kind of residual distribution is still a Gaussian. However, now the sigma itself here is depending on time, and it automatically chose a log link for the sigma to ensure that sigma stays positive. And here, classically, we get an intercept for the response and the slope with time, and the same for the sigma. Both of them are also depending on time now. And again, if we just plot the deterministic part of the model, we don't see much of a difference, right? Because the deterministic part doesn't include sigma anyway. However, if you then plot the posterior predict, including also the standard deviation of the residuals, you see, okay, this is much better reflected. Right, so you have like correct identification here and here. And I actually don't know if there was much of a difference in time here. It looks like it was almost the same. Here, so the confidence interval was this. The other one, let me check. Yeah, maybe there wasn't a strong difference here. At least none I can see currently. Yeah, okay. Maybe for this specific example, there wasn't much of a difference. However, if I do a model comparison, I will see that the new model represents the data much better. Okay, we get a warning. Okay, so we get a warning if some of the observations doesn't fit this quite nicely, but here it's just one observation out of a couple of hundred, so I don't mind. So I can trust these values. Okay, the new model here performs much better than the other one in predicting new data points. Okay, so here I compared the classical linear model, which has a normal distribution as a residual, with another model which has also normal distribution as residuals, but the standard deviation can change. Because both of them are continuous distributions for continuous response, I can compare them. What I can't do is I can't compare one of these to the previous models with the Poisson. Actually, I don't know what happens if I do it. Maybe I hope it will throw a warning, but I'm not sure. I will try now. Right, so this would not make sense. Right, so this is a negative binomial for a discrete response, and this is a distributional model here for a continuous response. Yeah, we'll give some values, whatever. Okay, I will get one warning, not all models have the same y variable. But it doesn't throw an error, right? So you could easily do this and just oversee this and say, oh yeah, okay, I fitted the one against the other and the one was better. However, this comparison mathematically just doesn't make sense. So please be advised not to compare models with discrete residual distributions to models with continuous residual distributions. Okay, then the next one is given as an exercise. So there is field data and field experiment where you have different seeds planted and the predation rate on the seeds is measured. The seeds are of different size classes. So the model is here, or this part of the model is, yeah, how predation rate is influenced by a size class of the seeds. Yeah, and I mean, there's just two types of observations: predation, yes or no. So this is a classical logistic regression type of analysis, and you can start here with this kind of model, or it's log of seed weight, which is the predictor. So this is kind of basic of the model, the base of the model. However, the interest is in another predictor, but let's go to the second one first. There are different locations, so you can test if, yeah, this predictor topo, which is a categorical predictor for location, if this has an influence. And also, that's the last part, if there's an influence on time. So this is a continuous predictor then. Oh, no, sorry, it's also a categorical predictor. There's, I think, 6 different sampling campaigns, and this is encoded by time. And related to this data set in this book was the question is, or the hypothesis in the, if the predation rate reaches a stable value in the last 3 time periods. So, I mean, you don't see it here because you're just plotting predation versus log seed weight, and these other predictors involved. So, yeah, you can use the predictor time here and use the EM means package to extract the means at the mean predation rate at different time points, and also their differences. So that's the important thing, looking at their differences to answer this this research question here.